Hello there, welcome to my channel on chemistry lessons. If this is your first time, welcome. If not, welcome back. But this channel provides material, full lesson material and revision material for all chemistry topics. I aim to be uploading regular videos to help and support you with your A-level chemistry as well as your BTEC applied science. So please subscribe so that you don't miss out on future videos, and also use the comments features to let me know of topics that you think would be useful in the future. Good luck, and I hope it's useful. This is an AQA A-level chemistry video, and it will focus on Spec point 3.1.11, which is an A2 physical chemistry. It's lesson 1 in a series of 3, and we're going to introduce the term half cell or electrodes, and we're going to look at cells and cell notation. The specification for this topic is fairly large. There's quite a lot going on. This will all be covered in a series of 3 lessons. Before you start though, it is worth making sure that you're up to speed with your 3.1.7, which is an AS topic on your redox topic, oxidation and reduction. Because without those fundamentals, this is going to be a really difficult topic. Okay, so make sure you brush up on those terms and how we assign oxidation numbers and how we can combine half equations. And this lesson is going to focus on those first 2 spec points, which is looking at what half equations are and looking at half equations for electrode reactions. We're going to look at what electrodes actually are, and then we're going to look at the conventional representation of cells. So let's look at what an electrode is. An electrode is a conductor of electricity, and it's where the exchange of electrons will take place. And you may recall from GCSE that you looked at cathodes and anodes. Now we won't use those terms in this section. We're just going to look at what actually happens at the electrode. So we're going to look at 3 types. We're going to look at metal electrodes, we're going to look at gas electrodes and redox electrodes. Now they all have the same thing in common. And the same thing in common is the fact that we have 2 oxidation states of the same element in contact with each other. So here we've got a piece of copper, which has the oxidation state 0 because it's an element. And we have a copper sulfate solution down the bottom, which will contain copper 2+ ions. So at this boundary here then, you've got the same element in 2 different oxidation states. You've got copper 2+ and copper as an element. So we've got oxidation state +2 and oxidation state 0 in contact with each other. So let's take a close-up look at that boundary then. So when it's an element, we've got metallic structure. It's copper metal. So we've got metallic structure here, which is the regular arrangement of positive metal ions and a sea of delocalized electrons. And that's fixed in lattice. You can see there by those 9 copper ions with the delocalized electrons. And on the outside, we've got these copper ions that are free to move. Now, what happens is we actually have an equilibrium that is set up. Some of these copper 2+ ions have the ability to move to the metal boundary and actually gain their electrons, gain 2 electrons, and become a copper atom and become part of that metallic structure. But what you've also got is the ability for these copper ions in the lattice to move into the solution and lose, therefore leave those electrons behind, lose those electrons. So you've got copper ions being reduced and copper atoms being oxidized. So we've got an equilibrium established. Now in some cases, this equilibrium may lie on the left, which means the copper is going to lose electrons more readily than it's going to gain them. So that copper will lose electrons, which means that you'd get a build-up of negative charge on the boundary because you would be losing these ions into the solution and therefore flipping the balance between the 2 pluses and the electrons, because you've lost 2 pluses, leaving the electrons behind, so you have an excess or build-up of electrons on the boundary, and therefore we would say that it would have a negative potential. However, if equilibrium was to lie on the right, that means that there's a greater tendency for the ions in the solution to actually join the lattice and therefore you get a build-up of positive charge around the outside because you'd have your 2+ ions forming around the boundary, and that would be known as a positive potential. Okay, now let's take a look at a gas electrode. So a gas electrode, if they're on the left here, this is a gas electrode. It looks quite complicated, but remember the key point is we have the same element in two different oxidation states. And if we look at this, we have hydrogen gas being pumped in and bubbled through the solution. And we have hydrogen ions in the solution. So this electrode on the left, we have H2 and H+. We have oxidation state 0 and oxidation state +1 in contact with each other in the solution. This is gas being bubbled through the solution, and this is H+ ions in the solution. So here we would have an equilibrium set up between the two, H+ and H2 gas. Let's balance that out. That's a half equation. Note we always show the reduction as the forwards reaction, always. So we'll always show the reduction as the forwards reaction. This one on the right hand side, let's take a look at what's happening here. So what do we have? We've got two different solutions being mixed together. Now, if you were to use your skills on assigning oxidation states, you will work out, or you will determine, that actually we've got the iron as 3+ from the top one, assigning your oxidation rules. And in the bottom one here, FeSO4, we've got iron 2+. So we've got two oxidation states here, 3+ and 2+. So this electrode will not be iron. We don't want three different states, three different oxidation states. So in the case where you don't have a metal as one of your oxidation states, or one of your parts of this, you're going to need a platinum, because we still need an electrode in order to measure this electrode potential. So we still need an electrode. We still need somewhere where the exchange of electrons can take place. So we'll use a platinum electrode. Similar over here, we used a platinum electrode because we need somewhere for the electrons to be exchanged. Okay. In your metal half cells or your metal electrodes, you literally used the metal as the electrode, and that's where the electron exchange would take place. But where we don't have a metal present, so H2, H+, Fe3+, Fe2+, they're not metals, so we need to have a metal for the exchange to take place, and that will always be platinum. Just to finish the half equation here then, so we're going to show the forwards reaction as the reduction. So 3+ plus an electron, reversible, Fe2+. So that would be our half equation for the electrode on the right. Okay, so what happens if we were to connect two electrodes then, or two half cells? Electrode or half cell, we can use those terms interchangeably. So on the right hand side, I've got a copper half cell or a copper electrode. There we go. So I'm going to show my forwards reaction as reduction. There's my reduction equilibrium. And on the left hand side, I'm going to have a zinc electrode or a zinc half cell with a zinc 2+. And again, my forwards reaction will be the reduction reaction here. Now, what will happen is if we combine the two together, now what we've done is we've connected them together with a wire across the electrodes, so to allow electrons to flow through this wire, and we're going to measure a potential difference with a voltmeter. So here we've got a wire, and we've got a wire connecting the two electrodes together with a voltmeter. And this in the middle here, this is known as a salt bridge. Now the salt bridge, it connects the two solutions together and allows charge to flow. This time it will be ions that flow, and it doesn't allow the solutions to mix. So this salt bridge connects the circuit by allowing ions to flow, but the two solutions do not mix. So your salt bridge, the easiest way to do this in a lab would just be to use some soaked filter paper with potassium nitrate. So we'll soak the filter paper with potassium nitrate and we literally stick the filter paper across both beakers so that it's in the solution, and it completes that circuit. It allows ions to move and conduct. So it completes the circuit. Now, by connecting those two half cells together, what we're going to do is we're going to have a potential difference. One of these half cells will lose electrons more easily than the other one, and vice versa. One will gain electrons more easily than the other one. So as soon as we connect these together, one of these equilibriums will be reversed and one will go forward. So one of the substances will be oxidized and one of them will be reduced. So either copper will gain electrons, copper ions will gain electrons to become copper, and the zinc will lose them, or vice versa. And we're going to look at how we can make those predictions, because that's part of what we need to be able to do. But our focus at the moment is just looking at electrodes and connecting electrodes to make cells. Okay, so now we've made a cell. So we've connected two electrodes to make a cell. I think if you had to draw this out every time, it becomes, it's not exactly straightforward. So we come up with a simple cell representation, a way of drawing this. But quick check first. I suggest you pause the video and see if you can answer these 4 quick questions. Okay, identify the salt bridge and its role. Well, the salt bridge is this, and its role is to allow ions to flow and complete the circuit, to allow the circuit to be complete, and it does so by a soaked piece of filter paper or a gel. If you've got quite a posh one, it will be a gel, or it will be a soaked filter paper with potassium nitrate. So it does need to be soaked in an ionic solution, because that will allow it to conduct. We know that ionic solutions do conduct because the ions are free to move. So it's not just a piece of filter paper. It does need to be soaked in potassium nitrate. Number 2, what's the purpose of the voltmeter? Well, that's to measure the potential difference. What carries the charge in the salt bridge? That's ions. Ions carry the charge in the salt bridge. What carries the charge in the wire? That will be electrons. Okay, so we're going to look at cell representation. It's a shorthand way of literally drawing this diagram without having to draw the full diagram out. Okay, so just to remind us, this left-hand side was zinc 2 plus 2 electrons going to zinc, and the right-hand electrode was copper 2 plus 2 electrons, reversible copper. Now we always show the forwards reaction as the reduction. Always, always, and that will always be the case in our exams. Okay, so what I'm going to do, instead of drawing a salt bridge, I'm going to draw double line. So that's my salt bridge. And then what we do is for the right hand side, so I've now drawn my salt bridge, we're going to focus on the right hand side. You're going to put the oxidized version closest to the salt bridge, so the most oxidized version of the right hand side. Now the oxidized version is Cu2 plus. And then the reduced version goes on the far right. Now, because they are in different phases, we draw a phase boundary. So we draw a line, and that line is a phase boundary. It's showing that the copper 2 plus is in a different phase to the copper. We can put state symbols in if you want, and we can see the differences in phases, aqueous and solid. And then we're now going to look at the left-hand side, and we put the most oxidized form closest to the salt bridge again. And this time the most oxidized form is Zn2 plus, and that's aqueous. And then we have Zn solid. So again, we need a phase boundary. Okay. And once you've finished your cell representation, what you should find is on the far left is one electrode, and on the far right is the other electrode. Okay. And it's kind of what we should be doing is we should be putting the positive electrode on the right and the negative electrode on the left. Now, we're not aware of these things yet, so we can leave that for now, but we're going to have a little practice of a couple of different types of cell representation. Let's take a look at what we've got here then. So as you can see, the cell representation is down the bottom here. Far more straightforward and far easier to do than to draw that entire diagram out. So let's have a look at what we've got. We've got the salt bridge in the middle. There's the salt bridge. On the right hand side, we've got a copper electrode or a copper half cell, which means we've got copper 2+ and copper metal. And we always put the oxidized form closest to the salt bridge. That's what this ROOR is. It's reduced, oxidized, oxidized, reduced. The oxidized form is always closest to the salt bridge. So we've got copper 2+ and then copper solid. Phase boundary. So our electrode on the right hand side is copper. Yes, it is. Left hand side is a little bit more complicated then, because on the left hand side we've got a hydrogen half cell, which was our H2 and H+. Now the oxidized form was H+, that goes closest to the salt bridge. Then we have a phase boundary and we have our H2 gas. Now there's an extra element to this one. Look, there's an extra part on the end, and that's because we must have our electrodes on the very ends. And the electrode here is not H2 gas. H2 gas is not the electrode. We need an electrode, so we have platinum solid. There it is there. There's our platinum solid. So that goes on the very far left. And there's a phase boundary because, again, solid, gas, different phases. So that's slightly more complex, that one. Let's look at 4 different scenarios then. So this first one is going to be copper with copper 2+ and aluminium 3+. Over here we're going to have magnesium 2+ solution. We'll have silver electrode with a silver solution, and down the bottom here we'll have a zinc electrode with a zinc solution, and I'm going to have an iron 3+ and iron 2+ in the solution. There's going to be a mixture of iron 2+ and iron 3+ in there. And over here we're going to have hydrogen gas with a H+ solution, and this is going to be a silver electrode with a silver solution. So I'm going to go through the cell representation for these 4. You may wish to pause the video and have a go yourself, although on the next slide you're going to get 3 more to do yourself. So you may wish to pause now and have a go, and unpause when you're ready. Right, I'd always suggest we start with the salt bridge. So there's my salt bridge in the middle. Then we're going to look at the right and the left. So the right hand side, the most oxidized form is copper 2+, aqueous. Then we've got a phase boundary and copper metal. And that is my electrode. That's the right hand side finished. Left hand side, the most oxidized form, Al3+, phase boundary, Al solid. And those are the 2 electrodes then, an aluminium electrode and a copper electrode. That one's complete. Similar situation on the right then, salt bridge, oxidized form, phase boundary, reduced form, oxidized form, phase boundary, reduced form. Again, could add state symbols to this. Slightly more complex on the bottom left then, salt bridge. Now my oxidized form, Fe3+, and I've got Fe2+. Now they're not in a different phase, they're both in aqueous, so they are separated by a comma, not a phase boundary. Now what's the electrode on the right hand side? We must have an electrode, so we're going to use a platinum electrode. So we're always going to use a platinum electrode. There we go, solid. Left hand side, oxidized form, Zn2+, phase boundary, Zn solid. So there's our cell representation of the bottom left. Last one then, salt bridge, oxidized form, phase boundary, reduced form. Yes, that's my electrode. Moving to the left, oxidized form, H+, reduced form, H2. And H2 is not the electrode, so I need a phase boundary and a platinum electrode there. So that's those 4 complete. Okay then, 3 more. I'm going to give you some information. we've got zinc and a zinc 2+ solution on our left. On the right, we've got an iron and an iron 2+ solution. And here, we've got a hydrogen gas and H+ solution. And on this side, we've got a mixture of iron 2+ and iron 3+ in solution. And finally, we've got a magnesium electrode here with a magnesium 2+. And on the right hand side, we've got an aluminium electrode with an aluminium 3+ solution. So what I suggest you do is pause the video, and when you think you've done your cell representation or your cell notation, unpause, and we'll see the answers. Okay then, first one, salt bridge, Fe2+, phase boundary, Fe. Zn2+, phase boundary, Zn. Metal electrode, happy. Middle, salt bridge, Fe3+, Fe2+, must put them that way around because you must have the most oxidized at the left closest to the salt bridge. We need an electrode in this case, platinum. And on the left, H+, phase boundary H2, because H+ is solution, H2 is a gas, phase boundary, platinum electrode. And then finally, the one on the right, we've got aluminium 3+, phase boundary, aluminium. And on the left, magnesium 2+, phase boundary, magnesium. Okay, time to have a spec check then and see where we're up to and what we've done. So are you pack convention for writing half equations for electrode reactions? Yes, that's the idea, that you always have the forwards reaction as a reduction. Okay, so that's forwards reaction is always a reduction and it's an equilibrium. Conventional representation of cells, yes. Okay, so next lesson is going to move into looking at how we actually measure electrode potentials and what electrode potentials actually are, and using that standard hydrogen electrode. So look out for lesson 2. So that's the end of that lesson then. Hopefully you found it useful. What you really need to do now is go away and do as much practice as you possibly can on cell notation. So find yourself some worksheets, because as with all of physical chemistry, it's about practice, practice, practice. Okay, it's about understanding a concept and then just application, application. So good luck. If you've got any comments for me, please let me know. Don't forget to subscribe and look out for future videos.